All right, welcome back everybody. So over the last couple of videos we've been talking about orthogonal sets of vectors, and we are also in the midst of trying to compute these orthogonal bases for certain subspaces. And what we want to do now is find a way to make this a task for the computer. We want to find a way to organize this information in such a way that it is useful to us from a practical standpoint. So, to give you an idea of how we're going to move forward, the first thing that we should do is find a way to organize information. So let's see if there is a nifty way to compile the Gram-Schmidt process into one, shall we say, organizational system. And in this case, we're actually going to wind up with a factorization of a matrix, right? So let's see how that might actually happen, right? So our first observation is that if this arbitrary basis beta produces the orthogonal set gamma through the Gram-Schmidt process, then what we know for a fact here is that this guy, this first vector that we're going to choose, specifically if we make it so that that gamma is an orthonormal set, or no, it doesn't even have to be an orthonormal set. We could choose it to be, but this is just an arbitrary orthogonal set gamma. But that first vector, that R11 really should just be a 1, right? The only time where R11 would not be just a flat out 1 is if we were going to modify Gram-Schmidt in some way, okay? And sometimes we do, sometimes we scale U1 so that it is a unit vector, which is exactly why that R11 is there in the first place. We'll see how that manifests a little bit later. So very, very technically, I think what we should have here, instead of just a plain old orthogonal set, this should be orthonormal, right? And I think that will take care of a lot of issues down the road. But I digress. The first step in that process is to make V1 equal to some multiple of U1, right? So we're going to choose U1 accordingly with V1. And from there, we can rewrite V2 as a combination of U1 and U2. Okay, so V2 is by design going to be the difference, or sorry, that U2 is by design, or some multiple thereof, right? The multiple R22. This is exactly what we were seeing before, that there's just some multiple of U1 that I'm shaving off of V2. Right, and so this shouldn't come as a surprise, right? This is exactly how we constructed the orthogonal set with Gram-Schmidt. And we can continue, right? There would be a V3 that only depends on, what, R31 U1, R32 U2, R33 U3, right? V3 is going to depend on these first three vectors from gamma. Just by design, that's how we're constructing the U set, right? And we can continue that each one of these vectors from here on out is some linear combination of the U1s up to that index. And in the final row here, we're going to have to use all n of these vectors from gamma in order to reconstruct Vn. So the original basis can be expressed as a lower triangular system of the new system gamma, or the new set gamma. And in particular, we already know what the values of these Rij's is going to be, because that's our orthogonal decomposition, or our orthogonal coordinate theorem, right? So we know exactly how to compute these guys in practice, and moreover, if gamma is orthonormal, then we can just go ahead and omit that denominator entirely and see that, oh sure, this is very nearly a Gram matrix. It's very, very close to a Gram matrix, right? The only problem is this guy is lower triangular and definitely 0 above the diagonal, so that means that this isn't a symmetric matrix, right? Or that these entries Rij do not make a symmetric matrix. Okay, so what we have to do in this case, if we're going to continue with this idea, we can just as easily compute the lengths of these VIs through our generalized Pythagorean theorem. Right, so if we go back to our orthogonal expansion, our orthogonal coordinate theorem, we can write the length squared of each of these VI vectors in terms of the Rij coefficients. Right, that's exactly what these guys are encoding. These are the weights that we have to assign to each of the U vectors in order to reproduce the V vectors. Right? And if this basis happens to be orthonormal, then we can go ahead and omit these guys because these are all 1. Right? Length squared is equal to 1. We get rid of all that. Okay. So we've introduced this idea that we have this Rij now, right? And we can go ahead and consolidate all these coefficients into one big matrix, right? So in order to produce this from effectively nothing, so if we're going to implement this in the computer, we technically should be building the basis U along the way. Once we know what each of these coefficients Rij looks like, we can actually build the Rij matrix from scratch, right? So we don't have to know what the U vectors are from or a priori. We can build them along the way. So this is exactly what's in this box. We are outlining this algorithm. That is the worst looking star. There we go. Right, this box is building our coefficients Rij, and once we have the Rijs, we can use them along with the U vectors we've already created to build the next U in the sequence. And if we feel like it, and in fact we should do this, we should scale down each of these U vectors to be unit. Right? This way we don't have to worry about any unnecessary divisions, which could result in dividing by very, very small numbers, which is very numerically unstable. So what we would like to do here is implement this exact feat, this exact set of instructions in the box. And what this does for us is it produces this lower triangular matrix R, which is given by the coefficients Rij. And then the matrix Q, right? This will be the matrix whose columns are the vectors of this orthogonal set. All right. So if we were to think of these guys as reproducing the original basis, right? That basis would be something that we could encode in a matrix, call it A, and then A would be exactly the following, where we have this R times Q construction, right? And you can double check this, right? If you multiply, say, the first row of R, that would be R11 and a whole bunch of zeros, dotted into U1 and a whole bunch of other vectors, well then the first thing that I see in A, the first column, is exactly R11 times U1. Sure enough, that was what we defined to be V1. If you go down to the next row in this matrix, right, I can kill off this little bit here. I'd have an R1, or not a 1-1, I'd have an R2-1 and an R2-2. Then I'd also have to consider the U2 vector in here. So the next element of my matrix would be R21 times U1 plus R22 times U2. And then so on. I can continue that. But the point is that this guy is now V2. So if I were to put the original beta basis into a matrix, then I could use this orthogonal coordinate system, this orthogonal set of vectors in the matrix Q, multiply that by R on the left, and I wind up with the original basis. Right? So I can decompose this matrix A in terms of this new basis, right? In a more familiar setting, what we actually see here is not the multiplication r times q, but we replace r with its upper triangular transpose, and we replace q with q transpose. And that flips the order on us a little bit, and we wind up with a new way of representing this matrix. Oh, wait, no, I didn't want to do that. Right, a new way of representing this as a q times r multiplication. And this is called the QR-Factorization of A. Now I say a QR-Factorization because we don't know this is unique, right? But if we have certain stipulations on the R matrix, then we can say for sure that this is the QR-Factorization of that matrix A. And we'll show that later on. But let me show you how this works in practice, how we're actually going to build this guy with a computer in mind. So let's start with something simple, right? We have 3 vectors sitting as a collection of independent vectors in R4, and R4 has the standard dot product as its inner product. And what we're going to do is we're going to implement the box, right? We're going to implement this box on the previous page. So R11, if I come back to this formula, R11, we need to start with just being the length of V1. And then U1 hat, we're going to construct an orthonormal basis. So we are going to divide through, or divide V1 by its length to get a unit vector at the end of this. So the first step here, compute the length of V1. V1 is this 1, 1, 1, 1 vector, which has a length of 2 in the standard Euclidean inner product, which would mean that V1 has to be scaled by 2 in order to produce a U1 hat that looks like this. Okay, nothing too strange here, but we have now picked up R11 in our matrix, and we have picked up Q, or U11, or U1 in this case. So U1 hat, done. Right? And that should actually be, so let me make sure I label these. So R is this guy, and Q is the first vector here, U1 hat. And that's all we have right now. That is all we have. That is not an Rn, that is an R11. Okay? What we need to do next is drop down to the next row, right? We need to figure out how to represent V2 in this space now. But V2 I can actually pick up pretty readily if I compute R21 rather. So I'm going to go to this step and start computing all of the inner products that I can get off of U1, right? So that'll be that'll be these 2 components here. So I know U1 hat and I know V2, so I can compute the inner products between those pairs of vectors. So this would be V2 inner product U1, and that winds up giving me 3/2, which now goes here in the R matrix. So R21 has been filled in. And I can also fill in R31. Right? It's the inner product of V3 with U1 hat. And V3 is sitting over here. I dot that with this vector down here, and I wind up with a grand whopping total of 1. How about it? So I now have filled in R31. I have filled in an entire column of R just off of figuring out the first orthonormal, or first unit vector in my orthonormal set that I would like to construct. Next, all right, that's exactly what we have here. Oh, yay, I'm tracking it. Good job, me. I'm tracking stuff in real time. Wonderful. Okay, so that's what we have so far. We have filled in 1 column of R and 1 row of Q. Okay, so Q still needs 2 more elements, or two more rows to be filled in. And the first one we can actually pick up with the information that we already have. If I go back to my box here, I can fill in R22 by asking, what is the length of V2, square it, and subtract off the lengths of, what would be R11? Yeah, R11 squared. Right, and I can do that, or R21, I suppose. Is that right? Yeah, R21 squared. Right, this is me in the step V2 equals, that U2 equals V2 minus R21 U1 hat. Okay, so this is the step that I'm sitting in as I compute R22, right? This is R22 right here, if I think about U2 as being a unit vector. So this is how long that difference vector is. Right, so V2 I can compute very quickly. Then this vector up here has a length of root 5, so I square it, and that's what I get for the first component here. That's the 5. And I subtract off, let's think about this, R21. R21 is this element here, second row, first column of the R matrix. And I'm squaring that and I'm subtracting it off of 5. Take the square root, and that's what goes in, take the square root, and that's what goes in R22. All right, so I now have, so if I'm filling this guy in, I have just figured out I have just figured out R22, so that's gonna fill in that next diagonal component of R. Great. And then that means I can go ahead and compute my U2 vector. But U2, remember, is going to give me some scaled vector, so I'm looking for a U2 hat, a nice unit vector at the end of this. So I'm going to get the difference vector first, and I have the information to do that, so it'll be V2 minus R21 times U1 hat, and I will have figured out what the second row of my Q matrix must look like, and it's going to be scaled thusly. So here's U2 hat. But I now have U2 hat, which means that I can go ahead and compute R32 based on this box on the previous page, right? I can keep going. I can keep building up this matrix. So I have filled in U2 hat right here, and my next aim is to fill in this boxed element in the R. And that's what this guy will be right here. It's the dot product of V3 with U2 hat. Cool. So feel free to slow down the video and go back and slow me down, like put me at half speed if you feel like it. But the point is for you to follow along with the computation, which at this point has filled in most of the R matrix and all but one row of the Q matrix. So for the last step, I have to figure out what is in this last diagonal element of the R matrix, which, as it turns out, we can follow the box, right? We can figure out what is this guy. In this case, it'll be V3 squared minus, I'll write it as a sum, no, R31 U1 hat minus R32 U2 hat. And those lengths technically should all be squared here, right? So really what I have based on, oh, you know what? Let me go backwards this way. There we go. Yay, now I don't have to worry about the box. Okay. Then what I'm really putting in here, this would be R31 squared and then 32 squared. Take the square root, and that's what goes in R33. Right, and this is all just following from our theorems about what coordinates have to look like when we use orthonormal bases. And that's exactly what we have in this last entry, right? R33 is just going to be that square root of V3 norm squared minus R31 squared minus R32 squared. All of this information we know, right? Here's 3,1, here's 3,2. Square both of those, take them off of the norm square of V3, and that's the square norm, or that's the square of R33. So take the square root of the result. Oh, shoot. I have to do those all over again. Whoop, there we go. Take the square root of that result, and you wind up with what has to go in this last entry. Okay? the last entry of R is going to get exactly the length of the resulting U vector. Not a U hat, but a U vector. Okay? So that being said, we can use R31 and R32 along with U1 and U2 hat to construct a U3 vector, but then we have to be careful because this is not necessarily a unit vector at the end. So we're going to have to take this guy, which is kind of a precursor to U3 hat, and scale him back by the appropriate length. And that'll be what we're doing in this step. We're taking U3 and dividing it by R33, which is exactly the length of R33 by design. So that will leave us with this unit vector. Okay, so we have now filled in the final row of Q with the last U hat vector. And we have completed the algorithm. We have orthogonalized the original basis, which was sitting back here. Right, we've orthogonalized the beta basis and created this pair of vectors, pair of matrices, excuse me, R and Q, or script R and script Q, and we can rewrite the entire beta basis as this matrix product. And this is the QR-Factorization that we've been looking for. All right. So in the next video, we're going to talk about how to use that matrix or use this decomposition once we have it. But bottom line here is that QR factorization encodes the Gram-Schmidt process. Right? So very much like the LU decomposition encodes Gaussian elimination, QR is going to encode Gram-Schmidt. Right? And this is kind of the theme for this class, that we're looking at practical linear algebra through the lens of factorizations of matrices. Now, these aren't just arbitrary factorizations. The factorizations come from particular algorithms, right? They're going to produce matrices with certain properties. And we would like to invoke these properties whenever possible, right? So this is what we're going to do in the next video. So until then, go through this video one more time. Make sure you understand what just happened to go from this matrix. Let's see if I can put it on the page. That would be 1, 1, 1, 1. And 2, 0, 1, 0. And minus 1, 1, 1, 1. Right? This matrix is now equal to this factorization of Q times R. Right? So that's the whole point. We are rewriting the original basis in terms of how we have to scale this orthonormal set of vectors. And that's the whole point of Gram-Schmidt. We now have an orthonormal, or a matrix whose columns are orthonormal, and we can recover the original matrix here on the left, excuse me, by multiplying this Q matrix into the appropriate weights that are living in this upper triangular R matrix. Cool. So go back, rewatch this video, make sure you understand how this process is working. Compare it against the box in this page. Make sure you're following along. My suggestion is to write it down. Actually have a pencil and paper handy so that you can go through and construct each and every one of these steps along the way. Right? So until the next video, right, we're going to go ahead